everybody in pre-calculus and trigonometry. This is what I hope is going to be our last week of covering some new material for our course. So we have two main objectives for this week. Today we're going to focus on that last content in Chapter 5. So there's two sections in Chapter 5 that we're going to try to touch a little bit on both of them today. Both of them are about rational functions. So last week we began our study of polynomial functions and looked at how powers of x shape the local and the global behaviors of the functions that they determine. And today we're going to stir quotient into that mix. So we're going to have one polynomial divided by another polynomial. That's what a rational function is. And so again, we're going to talk about what the local behavior of rational functions looks like, and then also the global behavior. So we're going to look at what happens near certain values of x, and then also what happens on the long run as x goes out to positive infinity, as x goes out to minus infinity. So we're going to focus on rational functions today. And as we roll into Wednesday, we're going to try and do the sort of last new material on trigonometry for the semester, which is about other trigonometric functions. So the reciprocals of the trig functions that we've studied so far, sine, cosine, and tangent, each have a reciprocal function. And then also the process of solving trigonometric equations. So we know how inverse trig works pretty well by now. How do we use inverse trig to help us to solve equations whose unknown is an angle inside of a trig function? So those are going to be the last topics. And then what I'm hoping is that that will free up the last 2 weeks of our course to just be working through reviews, working through quizzes, working through exams together, just sort of give the last assessments for our course, 2 or 3 weeks to breathe, and you have a ton of time to work on them and to get feedback from me. I'll get caught up on grading and all of that wonderful stuff. So one last push through the last content this week, and then we'll start reaching the finish line as far as the assessments for the semester go as we get into next week. So what are we working on today? Let me bring up the screen here. So rational functions. We have, again, these sort of two different types of behavior that we're going to be concerned with today. The first is what I call local behavior. How does one of these rational functions behave nearby to a certain x value? And with polynomials, when we studied them, the most important local behavior that we had were these zeros, the x-intercepts, the roots of a polynomial function. Rational functions, as we'll see today, have two other types of local behavior that we're really going to be concerned about. In addition to x-intercepts, or zeros, or roots, however you want to call them, we're also going to be able to look at when rational functions have vertical asymptotes. And what I think is kind of the most interesting local behavior that we'll see this semester, we're going to look at when rational functions have holes, what we call removable discontinuities in their graph, a place where the graph sort of stops and doesn't have a point right there, and then continues on as though nothing had happened afterwards. So these little moments of amnesia that a rational function has as part of its graph. So those are the important local behaviors we'll talk about that rational functions can have. And then we'll talk about end behaviors. With polynomials, just like with rational functions, the end behavior is always a question of what happens as x, or whatever my input value is. What happens is that value gets very, very large and positive. So as you go out to the eastern horizon of the Cartesian coordinate plane, what does the graph end up doing? What does the y value do as the x value blows up to plus infinity? And then likewise, when the x value blows up to negative infinity, what is the value of f of x, or the y value, going to be doing for a rational function? And unlike with polynomial functions, there's much more variety in the types of end behavior that rational functions can have. They can go off to plus and minus infinity like polynomial functions can, or they can settle down to a horizontal asymptote as x goes to plus or minus infinity. So we'll talk about when that happens, how we can tell when that happens for a rational function. And then, again, really interesting, what I think is one of the more interesting end behaviors for a rational function can also settle down to an asymptote, which is not a horizontal and not a vertical line, but which is a diagonal line, a slant asymptote, as x goes to plus or minus infinity, which is just another way of going to plus infinity or going to minus infinity, but it does so by settling down on a straight line. So we'll talk, hopefully, before we're done today, about when that happens and how to determine an equation for the line to which a rational function asymptotes as x goes to plus or minus infinity, using polynomial division. So it's a pretty ambitious agenda for the next hour or so, but we'll see what kind of justice that we can do for it. So I want to get our discussion started just by grounding us in what I call the 5 prototypes for rational functions. If we understand what these 5 simplest kinds of rational functions look like, then it's just going to be a matter of us spotting this kind of behavior across all kinds of different rational functions as we go along. So if we understand these 5 basic examples, then we'll be able to see these 5 basic phenomena happening in other rational functions as well. And so these prototypes are all going to be quite simple, right? The first set of prototypes are the functions f of x equals x and f of x equals x squared. These are functions that we know very well. These are polynomial functions. In fact, they're monomial functions, right? They're single powers of x. You learned what the graphs of these functions look like, back in your first algebra class, Algebra 1 or whenever. So years ago, you learned what the shapes of these graphs looked like. But then they also have reciprocals, the flip sides of those coins. If we just flip f of x equals x, take its reciprocal, we get 1 over x. X squared, we take its reciprocal, we get 1 over x squared. Those are going to be the 2 prototypes for rational functions that have the x's, the variables, in a denominator, where the numerator does not become 0 at some point. And then the 5th type, and this is, again, kind of my favorite, is what I get when I multiply this one and that one together. X times 1 over x, and I get a rational function that we might think of as f of x equals x over x. So these are my 5 different prototypes. And what we want to first understand is what local behavior, so that's what I'm most going to be concerned with initially, what local behavior do these prototypical rational functions have that we'll be able to then generalize when we look at the local behaviors of other rational functions down the line. So f of x equals x. It has local behavior that we are pretty well familiar with, right? It has an x-intercept here at x equals 0. And at that x-intercept, my graph, y equals x, crosses through the x-axis. And when it crosses through the axis, it looks like a straight line when it does, right? What we're seeing here is a function, f of x equals x, that changes sign from x's that are less than 0, in which my function is negative, to x's that are greater than 0, during which my function is positive. Right? So we have a sign change, and so we're crossing through the x-axis at that point. Okay? So f of x equals x is this prototype for a function which has an x-intercept at x equals 0 that this function's graph is crossing through as it passes through the x-axis. Meanwhile, f of x equals x squared has in common with f of x equals x that it has a 0, an x-intercept at x equals 0 also. But by contrast, where f of x equals x crosses through the x-axis at its 0, f of x equals x squared comes down to the axis and just barely touches it, and then changes direction to go back the other way. So it does this sort of touching and turning maneuver right at its x-axis. When we talked about this example in our last video, when we were looking at polynomials and their local behaviors, we called this a 0 of multiplicity 2, because this graph looks like a parabola. It looks like the vertex of a parabola when it touches the x-axis. Whereas this graph is an example of a x-intercept or a 0 with multiplicity 1, because this graph looks like a straight line, looks like a y equals x. In fact, in this example, it is exactly y equals x when it crosses the x-axis. So 0 of multiplicity 1, 0 of multiplicity 2. These are the 2 functions that sort of exemplify that local behavior near the x-intercept, which in this example is the x-intercept at x equals 0. Okay, so if that's the familiar prototypes for rational functions, those are the polynomial functions, what happens if I take the reciprocal of one of them? If I just take the reciprocal of y equals x, I get a function f of x equals 1 over x. And its graph looks like this. Right? So it has this feature where instead of having an x-intercept at x equals 0, instead of crossing through the x-axis at that point, when I take the reciprocal, what I'm really doing is I'm sort of turning the y-axis inside out. All the values which were close to 0, when I take their reciprocals, they're going to get very large, become much bigger than 0. They go out towards infinity. And then likewise, all the values of y that used to be really large, when I take the reciprocal, they become very small. And so taking a reciprocal really just takes that y-axis and just flips the whole thing inside out. So zeros become these new features that we call vertical asymptotes. So y equals 1 over x is a prototypical example of a function that has a vertical asymptote at the vertical line whose equation is x equals 0. I've just taken what used to be an x-intercept, and since I've turned the whole y-axis inside out, that x-intercept has turned into a vertical asymptote instead. So that's the first thing we notice, is that instead of getting an x-intercept, now we're getting a vertical asymptote. This is a place at which the denominator of my function's expression is becoming 0, but my numerator is not at that point. And so I'm going to get a y value here that looks something like 1 over 0. It's like I have one pizza to divide up, but the number of the size of each slice when I divide up my pizza is getting smaller and smaller and smaller. And the smaller that I make the slices of my pizza, the more people that I can feed with one slice apiece, right? And so as the denominator shrinks down to 0, the fraction 1 over that denominator is going to blow up to infinity. So that's why we're seeing a vertical asymptote near x equals 0. The other thing we notice about this asymptote is that the limiting behavior on either side of this asymptote is opposite. As x approaches 0 from the right side, 1 over x is going to approach positive infinity, right? Because 1 over a positive number is always going to be positive. And as that positive number gets closer to 0, 1 over that positive number is getting bigger and bigger and bigger towards positive infinity. On the other side, 1 over a negative number is negative. And the closer that that negative number gets to 0, the more that 1 over that negative number approaches negative infinity. So 1 over x is a prototype rational function that has a vertical asymptote at x equals 0, and the infinities that it approaches on either side are opposite to one another. On one side of the vertical asymptote, we're blowing up to positive infinity. On the other side of the vertical asymptote, we're blowing up to negative infinity. So we have this opposite limiting behavior. What about 1 over x squared? If I take the reciprocal of this, well, again, we're taking the y-axis and we're just turning the whole y-axis inside out. Everything that used to be close to 0 is now going to be close to infinity. In other words, way far up the y-axis or way far down the y-axis, depending on the sign. Everything that used to be close to infinity is now going to be close to 0. So this x-intercept that we used to have is once again going to turn into a vertical asymptote. And the difference between this example and the 1 over x example is that here in my vertical asymptote, we get matching kinds of infinity, matching limiting behavior on either side. Because of this square, because of the even exponent that I have in the denominator, my denominator for 1 over x squared is always going to be a positive number whenever x is not equal to 0. Right? And so on the right side of x equals 0, 1 over x squared is positive and getting more and more positive as x approaches 0. But then on the left side, when x is negative, x squared is still positive. And the smaller that x squared gets, the smaller that x gets, in other words, the closer to 0 that x gets, the more positive x squared, 1 over x squared, is going to become as x approaches 0 from the left. So when my exponent downstairs is even, we get these matching infinities on either side. So these are 4 of the 5 prototypes for rational function behavior that we can possibly see. And I want to actually save this 5th example. This is kind of my favorite one. I'm going to kind of deny myself for just a little bit. We'll save this example for maybe 20 or 30 minutes from now, but we do want to come back to the example of x over x because it has some surprises for us. But let's move forward into an activity for today's session. So this activity comes out of the Bulkin's Active Prelude to Calculus textbook that is the main text for our course this semester. And what it's asking us to do for a variety of rational functions. So by definition, by the way, a rational function is a function which is defined by an expression that results from dividing one polynomial function by another polynomial function. So when I divide x cubed minus 6x squared plus 5x divided by x squared minus 1, the result is what we call a rational function. So polynomial in the numerator, polynomial in the denominator. That's all that we mean by rational function. And so as with any type of function that we're meeting for the first time, one of the first questions that we have about them is what can we say, if anything, about the domain of those functions. And then we're going to ask questions about local behavior. So what can we say about the zeros, the vertical asymptotes of these functions, as well as the wholes, which we haven't quite talked about yet. And then the end behavior. What can we say about the horizontal asymptotes or lack thereof of these functions? So I want to take these one at a time. But you'll notice, first of all, that this third example is qualitatively different from the first example and the second example. And the reason it's qualitatively different is the way that we've expressed these functions is different. You'll recall from last week that when we were talking about the main local behavior features of a polynomial function, it was really important for us back then. Let me rewind the tape a little bit. It was really important for us to be able to use polynomial functions that were in their factored forms. Remember, we were able to discover the zeros and the multiplicities of this polynomial function and construct a sign chart that told me what the sign of this polynomial function was at various points. We were able to do that only because we knew what each of the factors was that comprised this polynomial expression that defined our function in the past. And the same thing is true here. When we have our polynomials in our numerator and denominator both in their factored forms, that's when we're going to be best equipped to discover what the local behavior, the zeros, the vertical asymptotes, and the wholes of these rational functions. We really, really want that factored form. So I'm just going to put that as kind of a universal caveat at the bottom of the screen here. Always, 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 when you're studying local behavior, always use the factored form. Factor your numerator, factor your denominator. Anytime that you're interested in the local behavior. The zeros, the x-intercepts, in other words, or the vertical asymptotes, or the wholes. We want the factored forms. So, because part E here, this third one of these three examples, because this part is already in its factored form, maybe the best way for us to proceed here would be to first talk about some basic features of that function, and then we'll come back to parts A and C afterwards. So let's first think about the question of domain. For what values of x am I able to plug in that value of x into this function and get a real number as the output? How do I know what the domain of a rational function is going to be? And why is this a more interesting question than it was when we were talking about polynomials? Well, a polynomial function, so if we just ignore the denominator for a second and just think about 19 times x minus 2 times x minus 3 squared times x plus 1, a polynomial function will have a domain of all real numbers. All real numbers all the time. Because for a polynomial, all that we're doing with our x, our input value, is we're perhaps raising it to some positive integer power, and perhaps multiplying it by some other real number, and then perhaps adding those results one to another. But there is nothing that could possibly go wrong when we do those things to any real number. So polynomial functions are mathematicians' favorites in a lot of respects because they are defined for all real values of their input. So the function as written here, if we forget about the denominator, this function has a domain that is all real numbers. The problem comes in the one arithmetic operation that we may not do with real numbers. The only arithmetic operation that is disallowed specifically in the real number system, and in fact in any field in mathematics, the only arithmetic operation we cannot do is we cannot divide by the number 0. That is the one thing we cannot do in arithmetic. Otherwise, addition, subtraction, multiplication, and division with any pair of numbers is possible, and it gives us a completely reasonable answer. The one arithmetic operation that is undefined is a division problem whose divisor, whose denominator, is equal to 0. So, the domain question is interesting for rational functions exactly because having a denominator opens up the possibility that that denominator could take the value 0 for some values of x. And it's exactly those values of x that make the denominator 0 that determine the values that we must exclude from all real numbers to discover the domain. So the first organizing principle that we have here is that the domain is going to consist of all values of x for which the denominator is not 0. For which the denominator is not 0. So if you can tell me, or if I can tell you, or if somebody on the street can tell us which values of x make the denominator 0, those are going to be the values that we need to delete from the real number system to discover the domain. Take out the values that don't work, and what's left are all the values that do work. So let's again start with this third question. How do I know what the domain of this rational function is? Well, I just have to focus on the denominator and ask what values of x make this denominator equal to 0. 17 times x plus 1 times x minus 4 squared times x minus 5. And here is where the factored form is our best friend. Because my expression here, my polynomial expression, has already been factored, and the right-hand side of this equation is 0, we can use the 0 factor property of the real numbers to split apart my factors and set each one of them individually equal to 0. And that is a fairly trivial algebra problem at that point. 17 times x plus 1, set that equal to 0. X minus 4 squared, set that equal to 0. And then x minus 5, set that equal to 0. Oops, don't need parentheses for that one. X minus 5, set that equal to 0. And then we just have to solve each one of those equations individually. Divide both sides of this equation by 17. That's just going to give me x plus 1 equals 0. And then subtract 1 rather from both sides. X equals negative 1. Take the square root on both sides of this equation, and x minus 4 is going to equal plus or minus 0. But of course, plus and minus 0 are both the same real number. They're both equal to 0. And now when I add 4 to both sides, I'll get x equals 4. And finally, x minus 5 equals 0. I can solve by adding 5 to both sides. X is equal to 5. So, what's the moral of this story? The moral of the story is that this rational function is going to be well defined. It's going to give me an output value, which is a real number, for any real input value that we give it, with the exception of those real inputs that make the denominator equal to 0. And those are exactly x equals negative 1, x equals positive 4, and x equals positive 5. So these are the values that I have to take away from the set of all real numbers in order to discover the domain. So how are we going to write our answer here? We could write it a few different ways. One way to do it would be to just use the set builder notation for it and write that the domain is the set of all real numbers x such that x is not equal to negative 1, is not equal to 4, and is not equal to 5. So that is one way of writing down the domain of this function. Just tell me which x's are disallowed, and then all the other x's will comprise my domain. If you want a picture of what this domain might look like, let's just imagine that we have the entire real number line. I'm going to make some space here so I can sketch this. Just imagine that we have the entire real number line from minus infinity to infinity, right? And we can color in that entire real number line as part of my domain, right? All of these real numbers, except that we are going to remove just 3 real numbers from this diagram. I'm going to remove negative 1. I'm going to remove positive 4. And I'm going to remove positive 5. So this is kind of a picture of what my domain is going to look like. It's actually going to consist of a union of 4 open intervals of real numbers. It's going to consist of all of the x's, all of the real numbers, from minus infinity to minus 1. So if we're keeping score, if you're keeping score at home, and you should be, let me move this over here. So from minus infinity to minus 1, we would call this interval minus infinity, comma, minus 1, with parentheses on both ends. Because again, we're not including negative 1 in the domain. And then this next piece, we would call negative 1, comma, 4, and again, with parentheses on both sides, because we're not including negative 1 in my domain, we're not including positive 4 in my domain. And then we'll have an interval from 4 to 5 with, again, parentheses on either side. And then we'll have, as our conclusion, the interval from 5 to positive infinity. All we would need then to do is include some union symbols in between to indicate that all of these 4 intervals together make up a single set, which is the domain of this rational function. So, either one of these examples is correct. It's just a different way of communicating the same information. The set of all real numbers except for the numbers negative 1, 4, and 5. And hopefully this example underscores the reason why we like the factored form. We didn't have to do hardly any algebra to solve for which values of x make my denominator equal to 0, because it was already factored. We just broke apart the factors, set each one of them equal to 0, and we were done. Recall that this was exactly the same as the sort of example that we saw at the end of our last class's video. So one of the ways of thinking about the domain is in thinking about, well, what can possibly go wrong? If I take 1 and I divide it by x plus 2, then the thing that can go wrong is that the denominator can become 0, and it becomes 0 exactly when x plus 2 is equal to 0. In other words, when x is equal to negative 2. And again, here at x equals negative 2, there is no point on my graph, which is above or below x equals negative 2. So that point, x equals negative 2, is not a part of the domain of my function. Right? So we're seeing this vertical asymptote behavior that we were seeing in our prototype example of 1 over x from before. if I also add an x minus 3 factor into my denominator, then I get another place where something has to be deleted from my domain. X equals 3 has to be removed from my domain as well. Because if x is allowed to equal positive 3, it would make this factor of x minus 3 equal to 0. And if that factor becomes 0, it makes the entire denominator equal to 0, and that is exactly the thing that we need to avoid. It's exactly the one arithmetic operation that is undefined. Right? So having the factors in there let me determine when that denominator becomes 0 exactly without having to do much thinking. And so that is always the way that we want to go if we can go in that direction. So if I want to answer this domain question for my other two examples here, my first maneuver, should be to rewrite these functions in their factored forms, focusing first just on the denominators. So what about x squared minus 1? How do we factor x squared minus 1? Well, that's a difference of two perfect squares. And a difference of two perfect squares can always be factored as the product of the sum of their square roots and the difference of their square roots. X squared minus 1 is the product of x minus 1 and x plus 1. So there's that denominator in its factored form. Meanwhile, a second example here, if I try to factor its denominator, it's a quadratic trinomial, x squared minus 3x minus 18. And so we'll play the sum and product game, give me a pair of numbers which multiplied give me negative 18, and which added give me negative 3. And I can find such a pair of numbers with a little bit of thought. A pair of numbers that fits that bill is negative 6 and positive 3. If I multiply them together, the result is negative 18. If I add them together, the result is negative 3. And so here is a factorization of that denominator. And the denominator is all that we need to know if the question is just about domain. I just need to know which x values to exclude. And it doesn't matter what's going on in the numerator. As long as the denominator is becoming 0, we need to exclude those values. So let's do these two examples. So my first example, when does this denominator become 0? Well, this denominator is going to become 0 when x minus 1 is equal to 0. Why don't I highlight these as we go along? It's going to become 0 when x minus 1 is equal to 0. And x minus 1 becomes 0 at x equals positive 1. So we need to exclude x equals positive 1 from the domain. And the denominator also becomes 0 when x plus 1 becomes 0. And x plus 1 becomes 0 when x is equal to negative 1. So we have to exclude that value from the domain also. So we can finish just by making this into set builder notation. The set of all x's such that x is not equal to 1 and x is not equal to negative 1. And we'll call that the domain for this rational function. Same story for my second example here. X minus 6, well, that becomes 0 when x is allowed to be positive 6. So we need to remove positive 6 from the domain, or otherwise that value of x would make my denominator equal to 0, because it makes this factor of my denominator equal to 0. And then x plus 3, that's equals 0 when x is equal to negative 3. So we need to remove x equals negative 3 from the domain of this function. And there we have the domain for our second example. So the domain, as it very typically is in algebra and in precalculus, is a matter of excluding the values that don't work, so that all the other values that are left over do. And all we care about in the domain question is what is happening in my denominator. The only thing we need to rule out is the situation in which that denominator might become 0. Okay, so now is a good time for us to go back and think about, now that we know which values of x are a problem, which values are problematic, which values of x do not belong to the domain of my rational function. Now the question is, what is happening with this function near the points at which my function is undefined, near the points that we excluded from the domain? And what I really am kind of saying by that is, I'm kind of saying, what type of behavior do we expect to see exemplified by the graph of my rational function with, using these prototypes as our points of reference? And so there's sort of these 4 different types of behavior that we could see for one of the factors in my rational expression. We could see my rational function becoming 0 by crossing through the axis, Or we could see it becoming 0 by touching the axis and turning back around. Or we could see it having a vertical asymptote that has opposite infinities on either side. Or we could see it having a vertical asymptote that has matching infinities on either side. Or we have the fifth example. And so let's talk about the fifth example here, because I think it's time. The fifth example is exemplified by the product of y equals x and y equals 1 over x. If I multiply those two things together, I get a function that looks like y equals x over x. And you might look at that expression and say, well, x over x, that's just equal to 1, isn't it? And so shouldn't we see a graph that just looks like a horizontal line, y equals 1? Right? Okay. We could say that. The problem is it's not exactly true. Because it's not always the case that if you give me a number and I divide that number by itself, the result, the quotient, is not always equal to 1. It is almost always equal to 1. But there is a single value of x for which that is not true. And it's again the same problem that we've been talking about in the domain question. The problem is if the denominator is allowed to become 0. Because if the denominator is allowed to become 0, then x over x is going to be 0 divided by 0. What's the problem with 0 divided by 0? Well, having a 0 in the numerator of a fraction tends to try to make that fraction equal to 0. Having a 0 in the denominator of a fraction tends to want to make that fraction's value blow up, right? So we have these two opposing forces, a 0 in the numerator that wants to make my fraction equal to 0, and a 0 in the denominator that wants to make my fraction blow up to infinity. And without any more information, we don't really know what's happening with this expression. It can't be both. It can't be both 0 and blow up to infinity. It can't be both an x-intercept and a vertical asymptote, right? That doesn't make any sense at all. So what actually happens here? Well, we have to exclude x equals 0 from the domain of this function, because 0 divided by 0 is undefined. But the good news is, for every other value of x, for every non-zero value of x, x over x is just equal to 1. And so the prototypical behavior that we see for x over x is the graph of a function which is perfectly well-behaved and reasonable and is just equal to 1 everywhere, except it's missing this one little point at x equals 0. What we get at that point is something called a removable discontinuity, or, better known in colloquialism, as a hole in the graph. It's just this little teeny tiny gap that is so small your graphing calculators usually don't even show them to you, right? Because it's one missing real number with all infinitely many other real numbers that are around it still included. So to the naked eye, we're not going to be able to see it on a graph. And yet, it is still there. It's a missing point in the domain, and therefore it's a missing point on the graph. Because even if the numerator also becomes 0 at the same place where the denominator does, that 0 in the denominator is still a problem that makes my function undefined. So a removable singularity is the fancy name for it, or a hole is the nicer name for it. That happens whenever the numerator and denominator of a function become 0 at the same time, in the same place. Everywhere else, x over x is equal to 1, but at x equals 0, there's a gap. There's a hole in the graph. So what does this mean for the functions that we've been studying here so far? Let's see if we can kind of work that out. I want to go back to our little rational function toy that I've been playing with here. And again, I'll add a link to this little exploratory tool in the YouTube description that's below here if you want to play with this as well. So what happens if I have a function like f of x equals x plus 2? Okay, so this is nice, friendly, you knew how to graph this function back in Algebra 1, right? It's a line with a slope of 1 and a y-intercept of 2. What happens if I divide this function by x plus 2? Well, nominally, it looks like I would just get 1, but the problem is that that function cannot any longer be defined at x equals negative 2. Let's go into this different graphing tool here. So if I have x plus 2, if I have x plus 2 upstairs, this is what my graph ends up looking like. But if I then take that x plus 2 and I divide it by another x plus 2, I'm again going to get this function that looks an awful lot like x equals 1. The problem, though, is that the domain of this function is no longer all real numbers. The domain of this function has to exclude the value x equals negative 2. And so we get this teeny tiny little minuscule hole here at x equals negative 2 because the domain of this function is no longer all real numbers. It's all real numbers except for negative 2. And if I then continue, maybe, for example, by, let's suppose I take and I multiply this numerator, x plus 2. Let's say I multiply this numerator by something else. Maybe I multiply it by x minus 3 or something. So now I'm going to get a function whose graph looks an awful lot like, let me look at this expression for just a second that defines my graph. This expression, x plus 2 times x minus 3 over x plus 2, it looks an awful lot like I should just be able to cancel these factors of x plus 2. And if I do that, I get f of x equals x minus 3, which is the straight line. The graph has a straight line that we're looking at right here, right? Slope of 1, y-intercept of negative 3. The problem is that this x plus 2 in the denominator still means that we are missing a point from the domain of my function, namely the point where x is equal to negative 2. And so we will still have a removal of discontinuity, a hole in this graph, because the numerator and the denominator are becoming 0 at the same point. So this is another caution that I have about factored form, is that factored form is great. Just do not be too hasty to do any cancellation once you have everything in its factored form, because cancellation tends to obscure information. When I cancel a common factor, I'm going to miss the fact that where that factor in the denominator became 0, we have to be excluding that value from the domain. So what does all of that mumbo jumbo mean? Let's take and factor the numerators of my expressions as well, so we can kind of try and finally figure out what's going on with each of these examples at the level of local behavior. Where do these functions have zeros, x-intercepts? Where do they have vertical asymptotes? And where do they have holes in their graphs, if any? All right, so let's factor this. Let's do the second example first, because the factoring is a little simpler. If I factor this numerator, x squared minus 8x plus 12, again, it is a quadratic trinomial. And so I'm going to be looking for a pair of numbers, which when I multiply them together give me positive 12, and when I add them together give me negative 8. And again, a few moments thought should convince me that the pair of numbers that do that are negative 6 and negative 2. And so there is the fully factored form of this rational function. Let's do the factorization for my first example up here also. I'm going to want to pull an x out of this trinomial here because it has a common factor. All three of these terms have a common factor of x. And if I do that, then the leftover cofactor is going to be x squared minus 6x plus 5. And if I then continue by factoring this quadratic trinomial, I need a pair of integers, if they exist, whose product is 5 and whose sum is negative 6. And there is such a pair of integers, fortunately, namely negative 1 and negative 5. X minus 1, x minus 5. And there's a complete factorization of this one as well. So getting all of our rational functions totally into their factored form is how we're going to figure out all of the local behavior questions that we have about this function. Zeros, vertical asymptotes, and holes. So let's come up with our dictionary for how do we tell the difference between these different types of behavior. So what I notice in these prototypes is that the examples on the top half of the screen here, my x and my x squared example, these are places where the numerator becomes 0, but the denominator does not. And so that's where we get zeros, or x-intercepts. So 0 happens when the numerator equals 0, but the denominator is not equal to 0. Right? So that's what's going on in the examples on the top. The two examples on the bottom, 1 over x and 1 over x squared, those are examples where the opposite thing is happening. The denominator is becoming 0 at a place where the numerator is not becoming 0. And so there's no sort of stalemate like we had in the example in the middle of the screen here. Instead, we know for sure that the value of my function is going to blow up to plus or minus infinity. We're going to get a vertical asymptote where the numerator is not becoming 0 while the denominator is becoming 0. And so it's only when we get both of these things happening at the same time that we're in this middle situation where we might have a hole. And so a hole is going to happen in my graph only when my numerator equals 0 at the same place that my denominator is equal to 0. So that's the first thing that we require happen. But then also we'll notice that all of my factors that are becoming 0 cancel. Right? I can do all of my cancellation in my rational function, and after all of my cancellation is done, I now have a function which neither the numerator nor the denominator is becoming 0 at that point anymore. Right? If I cancel this x with this x, I'm going to be left with something which is just equal to 1. Not a 0 in the denominator, not a 0 in the numerator, neither 1. And so we have this plain old hole in the graph. So, taking a look again at the factors that we have happening here. What I'd like to do, actually in all of these examples, is do just a little bit of rearrangement. Because what I'm noticing are that there are some factors that we can already see are common to the numerators and the denominators of my functions. In my first example, I've got this factor of x minus 1, which is common to both the numerator and the denominator. And if I were to cancel, if I were to reduce the numerator and denominator by that factor, all of the offending factors would go away. And it's for that reason that this function is going to have a hole exactly where these pair of factors, x minus 1, are becoming 0. So I'm going to write that over here in my holes category. X minus 1 is equal to 0. When that happens, I have a 0 in the numerator and denominator with equal multiplicities in both. And so I'm going to have a hole in my graph at x equals 1. Same story for my second function. I have this common factor of x minus 6 in both the numerator and the denominator of this function. And they're there the same number of times with the same multiplicity. And so if I were to cancel the factors of x minus 6, I would then remove the discontinuity altogether. I would no longer have a 0 in either the numerator or in the denominator. So we'll have a hole in the graph of that function. And that hole happens when x minus 6 is equal to 0, or better yet, solve that for x. We find out that that hole happens when x is equal to 6. Head's in the way. Okay, what about my third example? And for this one, I do want to move my face out of the way. So just give me a second to move my big head to the other side. There we go. So for this example, we again have a common factor. It's not written directly above itself, so it's going to just kind of be a little askew here. But we've got an x plus 1, both in the numerator and in the denominator of this rational function, with, again, the same multiplicity in both. So that if I were to cancel them, all of the problems that would exist otherwise at x equals negative 1 are going to go away. So this is a hole in the graph when x plus 1 is equal to 0. In other words, when x is equal to negative 1. So there are the holes in the graphs of these functions. What about the vertical asymptotes? So going back to our classification, vertical asymptotes, and again my head is in the way, the joys of teaching on a screen. Here we go. So the vertical asymptotes are places where the denominator becomes 0, but the numerator does not. And so that's going to happen in our examples here. Say in part A, this x plus 1 in the denominator is becoming 0, but there's not an x plus 1 in the numerator that makes the numerator 0 at that same point. So this x plus 1 in the denominator, which is unmatched in the numerator, becomes the location of one of my vertical asymptotes. So x plus 1 equals 0 is where I get a vertical asymptote happening. Or, better yet, the equation of that vertical asymptote is x equals negative 1. Play the same game with our second example. This x plus 3 in the denominator is making the denominator 0 at a point, namely at the point x equals negative 3. Let me make sure to get this color-coded for those of you with color vision. X plus 3 equals 0. Solve that to get x equals negative 3. That is a vertical asymptote for this function because that factor of x plus 3 is making the denominator 0 at a place where the numerator is not becoming 0 because there's not a matching factor of x plus 3 upstairs to countervail the x plus 3 downstairs. Finally, our third example here actually has two factors in the denominator which are becoming 0 at places where the numerator is not becoming 0. So when x minus 4 becomes 0, the denominator becomes 0, but the numerator doesn't. And when x minus 5 becomes 0, the denominator becomes 0, while the numerator does not. So we end up with two vertical asymptotes for this function. X minus 4 is equal to 0, and so x is equal to 4 is one of them. And the other is where x minus 5 is equal to 0. So when x is equal to 5. Two vertical asymptotes, x equals 4 and x equals 5. So notice that just like the domain question, the question of the location of vertical asymptotes of a rational function is completely, almost completely controlled by the factors of the denominator. We only have to look at the numerator to answer the question about is it a vertical asymptote or is it a whole? And it's only a whole if there are exactly as many factors, or actually let me say it this way, it's only a whole if there are at least as many factors upstairs as there are downstairs of the offending factor that is making the expression undefined at that point. Otherwise, if there are more factors in the denominator than in the numerator, we end up with this vertical asymptote. And that's what happens at whenever this x plus 1 is equal to 0, whenever this x plus 3 is equal to 0, or whenever this x minus 4 or that x minus 5 are equal to 0. All right, I'm going to move my head back over here for just a minute. Maybe I'll move it a little further so we can still see all the rest of the work that we have there. Let's talk about zeros, the x-intercepts of these graphs. So where do these fractions become 0? Well, a fraction becomes 0 exactly where its numerator becomes 0. We see that going back to our sort of taxonomy, our field guide here, right? A 0 for a rational function happens when the numerator becomes 0, while the denominator does not become 0. And so if we apply that logic to these rational functions, our numerators are going to become 0 exactly for all of the factors that exist in the numerator which are not matched by an equal or greater number of factors in the denominator. So in my first example here, I have a factor of x minus 5 that is becoming 0 at a point, namely the point x equals positive 5. So x minus 5 is equal to 0, so x equals 5. And so x equals 5 is going to be an x-intercept of this rational function, because the numerator is becoming 0 at that point, but the denominator is not, because there's not a factor of x minus 5 downstairs. But then also, don't forget this little factor of x that's sitting out there in the front. That factor is meaningful as well, because that factor is going to become 0 exactly when x is equal to 0. Not much of an algebraic equation to solve in that example, but it's still there. We still get this additional x-intercept, because when x becomes 0, this factor is going to become 0, making the entire numerator 0. And since the denominator is not becoming 0 at that point, this becomes an x-intercept of our function. Same logic applied to our second function shows me that we're going to get a 0 where x minus 2 becomes 0. So this factor right here becomes 0 in the numerator, but is not matched by a corresponding factor of x minus 2 in the denominator. And so when x minus 2 becomes 0, my whole function is well defined and becomes 0. And so x equals 2 is an x-intercept, or a 0, of this rational function. And last and certainly not least, we have two factors in the numerator here that are making the numerator 0, namely when x minus 2 is equal to 0, so x is equal to 2. That's one of these zeros of this rational function. And also when x minus 3 is equal to 0. X equals 3. And so that is a sort of a complete way, a complete strategy for classifying all of the local behavior of rational functions that we might care about. And again, the key to this whole enterprise is coming up with the factored form of our rational function. Once we have the factored form, we're able to identify all of the wholes. Those are the places where the denominator becomes 0 and the numerator becomes 0 at the same place. Right? So after we cancel, we can get rid of, maybe another way to say it is we can cancel out all of the factors that are making the denominator 0. Let me add that into our little decision chart here. So we're going to have a whole anytime all of the factors in the denominator that are making it 0 are able to be canceled. All these 0 factors in denominator may be canceled because there is an equal or greater number of the same factor in the numerator. So that's how we know that we get a whole, right, as opposed to a vertical asymptote. So the wholes are usually what I look for first, right? Because once we've identified the wholes, we can go ahead and cancel. We can reduce our fractions as much as we wish, because then the questions of vertical asymptotes and zeros are much easier to answer. Because if I had answered the questions about the wholes first, I could have gone back in and forgotten completely about the x minus 1 factors in my first function, right? And I could have forgotten completely about the x minus 6 example down here. And I could have forgotten entirely about the x plus 1s in this example. So if you identify the wholes first, it lets you focus for the remainder of your time on just the features which we know are going to be making either a vertical asymptote or an x-intercept for my rational function. The vertical asymptotes being the factors that make the denominator equal to 0, and the zeros coming from the factors that make the numerator equal to 0. And that's a complete classification of the local behavior. So let's finish today's lesson by taking a look at end behavior instead. So now that we know what's happening near the places where our function is undefined, so near the gaps in our domain, we know what's happening. What is happening in the long run, in our end behavior, as x gets very, 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 very large, either toward plus infinity or toward minus infinity? What is really happening to the values of these expressions? And it's actually here that we don't want to use the factored form. So avoid factored form, if you can, for thinking about end behavior. Okay, and so all of the work that we did to factor a few minutes ago, let's just forget about it. It served its purpose. Right? We used all of the factored forms to figure out the local behavior, the zeros, the vertical asymptotes, and the wholes. But now what we can do is think about the end behavior by instead using the multiplied out forms, not the factored forms of these expressions. So I want to do this again by making an analogy to how we figured out the end behavior for polynomial functions in our last video. In our last video, we said that we could figure out the end behavior of a polynomial function by focusing only on its leading term. So that term in the polynomial that has the highest exponent on the x. Because as x gets large enough, all the other terms are going to diminish in size compared to that largest value. So what we did, for example, was I'm going to take this example right here, my second one, and we just took and factored out the highest power of x in my polynomial. And if I did that with my numerator, my x squared minus 8x plus 12, if I factor out an x squared, then the cofactor that's left over is going to be 1 minus 8 over x plus 12 over x squared. And the reason that we did that in our last video is that it helps us to think about what's happening as x becomes very, 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 very large. So as x goes out to positive infinity, what is going to happen to the value of 8 over x? Well, again, as we've been talking about today, when my numerator is not becoming either 0 or infinity, but my denominator is, that's when we know for sure, unambiguously, what's happening. As x goes to infinity, 8 divided by x is going to be the result of dividing up 8 pizzas among infinitely many people. And so the amount of pizza that each of those persons is going to get is growing arbitrarily small. So as x goes out to plus infinity, 8 over x is going to shrink to 0. And for the same reason, 12 over x squared is going to shrink to 0. And so in the long run, if what I care about is the end behavior, I'm just going to kind of write this here, as x goes to plus or minus infinity. So whichever side of the horizon we try to go to, the east side or the west side of the xy plane, these 8 over x's and 12 over x squareds, those are just going to sort of diminish. And so I'm going to focus just on that leading term, the x squared times 1, because as x goes out to plus or minus infinity, 1 stays 1. If I do that same factorization in the denominator as well, I'll get a cofactor of 1 minus 3 over x, minus 18 over x squared. And yet again, that 3 over x, as x goes out to positive infinity, that 3 over x is going to go to 0. And as x goes out to positive infinity, this minus 18 over x squared is also going to go to 0. And so in the long run, the end behavior of this function is that both the numerator and the denominator pretty much look like just x squared. And when I cancel these x squareds, when I reduce my fraction, the fraction reduces to a single number, 1. Let's see if we can figure out what that means for the shape of this graph. I'm going to go back to my rational function builder toy here that we've been playing with. So let's imagine that I have an x plus 2, and that x plus 2 is up in my numerator. Maybe I'll put it in there twice, just for fun. X plus 2, the quantity squared. And then let's imagine that I also have x minus 3, and I have it in the denominator. I wanted the denominator not once, but twice. X plus 2 squared, and then the denominator will have x minus 3 squared. So what I kind of noticed from this graph is it looks like the end behavior as we go x towards minus infinity, it looks like my graph comes down and it touches the x-axis right here, but then it starts to kind of lift off the x-axis again as we get a little further down the line. And if we could scroll out to the right, we might ask the question, well, what's this part going to do as x is going out to positive infinity? Let's take this opportunity to just go ahead and try to graph this thing. So that was x plus 2, the quantity squared, divided by x minus 3, the quantity squared. Get my parentheses in here, whoops. X minus 3, quantity squared. And so if I graph that thing, we've got to zoom out a little bit to see what's actually happening with the shape of this graph. So here we're seeing the behavior that we were talking about, right? It goes down and it touches the axis. And actually the hole, I got to fix where the hole is. I have to do this part manually because computers are not wise enough to put the hole in the graph. Just because the hole is so tiny, graphing calculators aren't going to show it to you. In fact, this hole is not even visible in this graph. Actually, it's not even a hole. Never mind. Let's not worry about that. So it comes down, it touches the axis, but then it lifts back up off the axis. And if we zoom out, what we see is that as we go to the right, this line doesn't look like it's settling down on the x-axis either. So there appears to be a horizontal asymptote for this function that is not just the x-axis, which is something different from what we saw with f of x equals 1 over x. Right? F of x equals 1 over x has a horizontal asymptote on the x-axis. So what is, in fact, the horizontal asymptote for this graph? It's going to be y equals whatever value that this expression tends toward as x tends toward plus minus infinity. So in this example, that horizontal asymptote is going to have the equation h of x, or y on my graph, is equal to 1. So let's put that into our chart here. So the horizontal asymptote for this graph is going to have the equation y equals 1. And it's because when I look at just the leading terms in my numerator and denominator, my leading terms are going to completely reduce. I can cancel both of the x squareds, and it leaves me with a real number, the number 1. That's an equation for my horizontal asymptote. What happens if I take that tack with my first example? If I look at just the leading terms of f of x equals this expression up here. Well, again, focusing on my leading terms means in the denominator I'm going to look just at the x squared. So I'm going to obscure all the algebra that we did to get here, and I'm going to just focus on the leading term and erase everything else. So the x squared in the denominator and the x cubed in the numerator. So what is this going to look like? This is going to look like x to the third divided by x to the second. That's going to look like x to the first, subtracting the exponents because we're dividing powers of a common base. But then as x goes to plus or minus infinity, f of x, which is equal to x, is also going to go to plus or minus infinity. So as x blows up to positive infinity, my f of x is going to blow up to positive infinity as well. So as we go out to the east end of the graph, my graph is going to crash through the ceiling. And as we go out to the west end of the graph, my graph is going to crash through the floor. Let's take the opportunity to just graph this function, and we'll verify that that's the behavior that we're seeing. Right? So my original graph here was f of x equals x cubed minus 6x squared. Sorry, let me get this. Too many clicks. F of x equals x to the third minus 6x squared plus 5x. And then I'm going to divide that by x squared. Let's take a look at a graph. And so what I'm seeing here is that as x goes out to positive infinity, as it goes to the east end of the xy plane, f of x is going to crash through the ceiling this way. Right? F of x is going to go to positive infinity. As x goes to negative infinity toward the west end of the xy plane, f of x is going to crash through the floor towards negative infinity. And so this graph does not even have a horizontal asymptote. So we'll just write in here, horizontal asymptote, none. Right? Because it doesn't settle down, the graph doesn't settle down on a horizontal line. This function's y value, f of x value, does not tend to a constant number as x goes out to plus or minus infinity, as was the case in our part C, in this function, right? This function settled down on the constant number 1. This function doesn't settle down on a constant number at all. It blows up toward plus or minus infinity. And so, this function does not have a horizontal asymptote. What it does have, however, is a different kind of asymptote. If we take a look real quickly at this graph one more time, it looks as though this graph is tending toward a line as x goes to plus or minus infinity, but that line is not horizontal, right? It doesn't settle in on a constant value, but it does seem like it tends toward a straight line. Can we find an equation for that straight line? I thought you'd never ask. Here is a way that we can actually find an equation for the line, the slanty line that this graph tends toward as x tends to plus or minus infinity. Since the line is not horizontal, we call this an example of a slant asymptote. So this will be our last thing that we do today. How do I find the slant asymptote for this graph? To do that, we're going to borrow from a technique that you may have had some exposure to at some point. It's not going to be a center point of our course, so I don't know that I'm even necessarily going to ask that you do this. But I think it's a valuable exercise anyway, and we may have occasion to do it later on down the line, maybe in calculus and maybe in our course. So what this technique has us do is actually do a division problem. I want to divide x cubed minus 6x squared plus 5x. So let me put in my coefficients here. 1x cubed, negative 6x squared, positive 5x. And then let me also put in here a fictitious coefficient of 0 times 1. So I want to put in a bunch of coefficients here, plus 0 times 1. And then we are literally going to do a long division problem. 5th grade style. I want to divide my numerator, right, my dividend. I want to divide my numerator by my divisor. And my divisor is x squared minus 1. So I'm going to put x squared minus 1 out in front of this division symbol. X squared, 1, and I'll put the fictitious coefficients in front of it also. 1 times x squared plus 0 times 1. Okay, so I want to divide this into that using the ordinary long division algorithm that you learn in 4th grade or 5th grade, or whenever it is that you learn it. We're just doing it now with, in place of the place values of ordinary numbers, where the role of the x here is going to be played by the number 10. Now, the role that place value is replaced by are the various powers of x. So how it works is we're going to take the leading terms, so x squared in this example and x cubed, and ask how many times does 1x squared divide into 1x cubed? And for that, the quotient is 1, that's the quotient of the coefficients, times x to the power 1. That's the quotient of x cubed divided by x squared. How many times does x squared go into x cubed? It's the kind of question that we ask a lot when we're doing factoring problems. And after all, factoring is nothing more than fancy division. So we'll call that quotient just x. And then, like with any long division problem, we'll multiply this x by my divisor, x squared plus 1, and write that product underneath what we had before. So x times x squared is going to give me x to the power 3. Did I just lose my pencil? Oh, there we go. I'm going to get x to the power 3. And then x times 0 plus 1 is just going to give me a plus x. So I'm going to write that right here. So we multiplied this by all of that, wrote it underneath down here. And then, as with any good long division algorithm, our next step is to subtract. So I subtract 1x cubed minus x cubed, and my x cubes have gone away. And then I'll drop down minus 6x squared. I'm not subtracting anything from it, and so I'll get just minus 6x squared. And then I'll drop down this plus 5x minus x is going to give me plus 4x. And then I can drop down this 0 times 1. That's just going to be 0 again, so I'm not even going to write it. And then we play the game one more time. How many times does 1x squared plus 0 times 1 divide into minus 6x squared plus 4x? Well, again, compare the leading terms. How many times does 1x squared go into minus 6x squared? And that quotient is just minus 6. And again, we play the game of multiplying that term that we just wrote down by my divisor. Minus 6 times 1x squared plus sorry, why do I have a 0 there? I wanted a 1 there. Apologies for that. Right, so x squared plus 1. No, x squared minus 1. Oh boy. X squared minus 1. So now I need to make sure that the example we did before still works. Nope, it doesn't quite work. So sorry about this. Let me go back and repair the mistake that I made. So this is going to become plus 6x here. Oh, glad I caught that. Okay, let's try again. So negative 6 times x squared minus 1. Negative 6 times x squared is going to give me negative 6x squared. Negative 6 times negative 1 is going to give me positive 6. And then I just have to subtract that amount from the line that's above it. Negative 6x squared minus negative 6x squared. My x squareds are going to go away. My 6x does not have a match, and so subtract 0, it's just going to drop down. And then I've got 0 minus 6 from the line above it. I'll get 6x minus 6. And now, since my x squared cannot divide into my 6x anymore, this thing that I have down here at the bottom becomes my remainder for this division problem. So it's x minus 6 with a remainder of 6x minus 6. Okay, so all right, that's kind of a hokey little algorithm, right? What does it actually do for us? What it does is it allows us to rewrite this expression which defines my function. I can rewrite it as a quotient plus a remainder. Where does my quotient come from? My quotient is the thing in my long division problem that is not a part of the remainder, x minus 6. So that becomes my quotient, x minus 6. Now, let me color code it again, x minus 6. And then after that, I have a remainder. And the remainder tells me how many denominators that we have left over after we have divided the numerator by the denominator. And so my denominator, x squared minus 1, still remains down here. And the numerator, how many of them we have, is where my remainder goes. So how does this help? This helps because now I have a piece, this remainder piece over here on the right. We know for sure that as x tends to plus infinity or x tends to minus infinity, this thing is going to look like the ratio of its leading terms. And the ratio of its leading terms looks like 6x over x squared, for which we can reduce the powers of x to look like 6 over x, which as x tends to infinity just looks like 0. So the moral of the story there is as x tends to plus or minus infinity, my function is going to look like x minus 6, even though on the nose it is equal to x minus 6 plus this additional stuff, right? So my function is exactly equal to this expression, but as x goes out to plus or minus infinity, this extra term just sort of looks unimportant. It just shrinks down to 0. And so the graph of the function y equals x minus 6, that we know how to graph. Y equals x minus 6 is a diagonal line with a slope of 1 and a y-intercept of minus 6. And if there is any justice in the universe, that function, f of x equals x minus 6, we believe should be the slant asymptote for this function, because the difference between our original function and the function which defines my slant asymptote, that difference becomes closer and closer to 0 as the further out that we get towards plus or minus infinity, because that difference is exactly equal to this remainder, 6x minus 6, divided by x squared minus 1. So this whole piece shrinks down to 0 as x goes to plus or minus infinity. Right? So let's find out if that actually works. Here's the graph of my function. What's going to happen if I also graph y equals x plus 6? No, sorry, x minus 6. Sure enough, y equals x minus 6 is exactly the diagonal line to which my rational function approaches as x goes out to plus or minus infinity. And so that's what we call the slant asymptote of this function. How did we get there? We just had to do a division problem. I had to divide my numerator by my denominator using a polynomial division process. Here I use the process that's called polynomial long division. You can find a lot of resources out there on YouTube or out there in the sort of the math teaching universe to give you some more examples of what that looks like. There's also a process that sometimes can be used called synthetic division. It's not my favorite to use in these kinds of examples, but you certainly could. And so the point is that this thing is a slant asymptote for my function because the difference between the function itself and this asymptote, this difference is equal to 6x minus 6 over x squared minus 1. And so that difference gets smaller and smaller. The gap between the graph and the asymptote gets smaller and smaller and smaller as x tends out to plus or minus infinity. So that's going to do it for today. We had an opportunity today to look at both how we can use the factored form of a rational function to determine the local behaviors, and also how to use the non-factored form, just by looking at the leading terms, to determine the end behavior, horizontal asymptotes. And then also how polynomial division can help us to find when a rational function has a slant asymptote as well. We're going to, in our next session, move on to talk about the last trigonometry topics for the semester. Those are going to be an introduction to the 3 reciprocal trig functions, sine, cosine, and tangent. Each have reciprocals called secant, cosecant, and cotangent. And we'll also talk about how to use inverse trigonometry to solve trigonometric equations and find all values of their solutions. And that is going to do it for the new material for the semester. We're going to shift gears after that and move into the sort of an assessment and feedback cycle that's going to extend through the end of the semester, quizzes and exams, and a process of getting your feedback on your work. The web work problems for those of you in my class this semester remain open all the way through the end of the semester, so now is a good time to work on the web work for the rational functions chapter that is up there, and then as we move into the trigonometry next week, those ones as well. So I will see you back one more time in a couple of days for yet some more new material, and then after that, as we get into next week, we'll shift gears and focus mostly on assessments, quizzes, and exams, and we'll do some live streams like we've been doing, but we'll populate those with review questions and try to make those responsive to the questions that you're most interested in seeing. So I look forward to seeing you then.